If this falls out of kilter, adjust it. Don't let it die. All right, so this is theory of computation. I see a lot of familiar faces. How many here had a course from me before, like in algorithms? Okay. So we'll talk a little bit about the overlap in the readings and so on when we get to it. But, so you've seen this problem before, right? The centrifuge problem. Those who haven't, how do you balance 5 test tubes in a 12-hole centrifuge in a balanced way? And we'll talk about that a little bit later, but since most of you have seen it before, we'll breeze through it. We're going to use this textbook here, Sipser, Theory of Computation. And it's a very good book. It's in the 2nd edition, is the one we will use. There's a 3rd edition, but it's more expensive, and it's almost the same as the 2nd edition, so we will still use the 2nd edition. It's plenty good. Theory changes very little, very slowly, so not a whole lot of change in that over time. There's lots of articles and videos. Most of you are familiar with that. We had my class before. And if you haven't read that book yet, it's always a good idea to read it. Even if you read it, it's probably a good idea to reread it. But it's a classic on problem solving. One should probably read it every few years anyway. It's so good. The algorithms book, extra readings, or if you want to brush up on algorithms, that's always a good book. You've seen that book if you were in my algorithms class. In fact, this book is so good, I even have an endorsement on the back of the book by yours truly, so I can tell you it's good, it's official. So we'll start by going through a brief history of computing. By that I mean we'll go from first principles, we'll go all the way back to Aristotle and Euclid and Archimedes and all the way through Gauss, Boole, and Babbage. I highlighted some of them in red because they're more central to computer science, but it all builds on work and on discoveries and insights by previous great thinkers throughout history. And we'll talk a lot about these people and their contributions and how it ties to theoretical computer science and how it forms the foundation of not just computer science, but all mathematics and science in general. So as far as more specific things, we'll review automata theory and languages, talk about two-way automata, generalized automata, infinite automata, deterministic context-free languages and context-sensitive languages, ambiguity in grammars, non-determinism and alternation, which is even a generalization of non-determinism. Non-determinism is a term of generalization of determinism. And we'll talk about the Turing test and AI in general. By the way, this is a Chomsky hierarchy over here, and this is kind of a central map of all the material for this course, showing you a Venn diagram of containments between these classes of languages. Some of these containments, whether they're proper or not, are open problems. For example, we don't know if P is a subset of NP properly. We know it's a subset, but not a proper necessarily subset. That's an open question worth literally $1 million from the Clay Institute. And then we'll go into undecidability more deeply, reducibilities, computational universality. DNA computing is an example of universality of computation. The Game of Life by Conway, cellular automata, special case, also a nice example of universality of computation. We'll talk about oracles or organizations, Turing degrees, randomness, entropy, lots of cool, interesting topics. We'll talk about complexity classes and the complexity hierarchy, about density and gap theorems related to complexity classes, axiomatic complexity, all sorts of theorems that relate complexity classes to one another. And then later in the course, we'll talk about NP-Completeness and approximation algorithms. This will overlap with some of the stuff that we talked about algorithms, but maybe here we can go into it more deeply or look at different examples. So that's sort of the roadmap for this course. And this is an example of a Venn diagram involving number systems. Obviously, the integers are contained in the rationals, which are in turn contained in the reals, and the real numbers are contained in the complex numbers, but there's lots more outside that. There's numbers that are quaternions, or generalizations of complexes, where you have I, J, and K all being the square root of -1, but not equal to each other. Multiplication is not commutative in this algebra. Then outside you have octonions, sedentians, surreal numbers, and that's even tricky to define. Anybody heard of surreal numbers here? All right, let me try to define that because it's so cool. You can define every number class strictly on the basis of the lower number classes. So for example, you can define integers as the naturals union with all their additive inverses. That is the negative numbers, right? So you can define reals strictly in terms of naturals. Right? And then you can define rationals strictly in terms of integers, by saying a rational is a quotient of two integers. That gives you the rationals. How is a real number defined in terms of rationals? Any thoughts on that? How would you define a real number if all you knew about a rational number? There's a number of ways to do that. One of them is called a Dedekind cut. You can take the rationals, divide them into two sets. Say you try to define pi, which is a real number but not a rational number. Take all the rational numbers, divide them into two sets. One set will be all the rational numbers less than pi. The other set will be all the rational numbers greater than pi. Take these two sets as an ordered pair, and that uniquely determines pi. Pi is sandwiched exactly in the middle between these two sets, and it's a unique real number that does so. How many get that? Okay, so that's how you can define reals strictly in terms of rationals. So that's called a Dedekind cut because you kind of slice the rationals into two separate, mutually exclusive subsets, all of which in one set are smaller than all of which in the other set. All right, so these are real numbers. So real numbers is just like that. It's a cut, except you lift the restriction that everything in one set is got to be strictly less than everything in the other set. They can be intermingled into two sets without any particular order, global order on them. That's a generalization of the reals. It contains all the reals plus a whole lot more. It contains infinitesimals, it contains infinite quantities as well. Infinitesimals are not reals, infinite quantities are not reals either. So that's, I just defined surreal numbers for you. Once you define surreals, you can define surcomplexes as A plus BI, where A and B are surreal. And lots of other number systems. So there's lots and lots of things beyond the complexes. How many knew that before? Okay, the rest of them, my gift to you. Just like if you just knew about the reals but not about the complexes, or just about the rationals, not about the reals, it's not a disaster. You'll still have a good life. It's just kind of a missed opportunity and kind of a little bit of a shame that you never heard about such things. So now you know about stuff outside the complexes, and there's plenty of stuff out there. Anyway, in this course, we'll prove lots of theorems. Here's a couple of examples. We'll prove that some real numbers are not finitely describable. Some real numbers, they exist, they're on the number line, but we cannot describe them in any finite way. Not using words, not using an algorithm, not using a formula, none. But they're still there and they still exist. It's interesting. Right now, at this point, of course, we don't have enough machinery to prove that, but within a couple of weeks we will. We'll also prove things like some finitely describable numbers are not computable. So some numbers are finitely describable, but there's no way to have an algorithm that spits out their digits, ever. An algorithm doesn't exist that has that property. It spits out its digits of some of these numbers. Again, right now we can't prove it. We don't have enough machinery yet. In a few weeks, we will prove these theorems and many more. Any questions so far? By the way, stop me if there's any questions or comments or thoughts. Or you want to look more deeply about anything. It's a graduate course, we can do that. So here's the Chomsky hierarchy again, reloaded. Imagine how much time and effort this slide took, basically a whole weekend with all the animations, making sure everything is just so. This is the Venn diagram, it's the set containment diagram. And we will study many of these areas of this diagram throughout the course. In fact, this is the roadmap to the whole course. We'll talk about regular languages, context-free languages, context-sensitive languages, then polynomial space, polynomial time, exponential space, decidable languages. We'll spend much time on each of these classes. And there's infinite hierarchies in between that we'll also allude to at some point. And this gets to be a very, very complex diagram. And even this diagram, as complex as it is a tip of a giant iceberg that's even bigger than that. And we'll talk about the complexities, so you'll see exactly what I mean. There's literally hundreds and hundreds of these classes. Here I'm just showing you a few dozen, a couple of dozen things. And these green things are examples of each element of a class that's not an element of the classes below it. So for example, the language A to the N, B to the N is deterministic context-free, but it's not regular. Right? And similarly for quantified Boolean formulas, it's a polynomial space complete language, but it's not polynomial time solvable, and so on. And there's languages which are recognizable, but not decidable. And there's languages which are not even recognizable. Don't worry about if you don't know what these terms mean. In a few weeks, you'll know what all these terms mean. and theorems about them and interrelationships among themselves, and so on, as complexity classes. But this is sort of, if I can only show you one slide that describes everything that's going on in this course, this is it right here. That's why this is part of the website for the class, very prominently as a picture. So we will focus on the scientific method, on the big picture. You know, since most of you took my course by now, you sort of know how I operate. You know, I kind of harp on fundamentals and insights and beautiful theorems and elegant ways of defining and explaining things rather than more esoteric, convoluted things. And never forget that having fun is the primary objective, because if you have fun, you'll do whatever it is you're doing better and bigger and be more interested in it. So as far as prerequisites, not a whole lot. If you know a little bit about discrete math, that's good enough. If you took this kind of complexity class in the past, that's also useful, but we will study here stuff that you probably haven't seen in the past, and I'll try to give that more attention and more time, rather than to stay on the beaten path. Tenacity is very important. As you know, solving problems is tricky business. If you spend just an hour or 2 or 3 or 5, it may not be enough. Some problems will take days to solve, some problems you will never get, becoming all sorts of levels of difficulty. But working groups, you know, form study groups of 2, 3, 4, 5 people at a time, that's good. There'll be a problem-solving session every Saturday at 3, and there'll be pizza served. My gift to you, it comes out of my own pocket, as you've seen in the algorithms course. We continue to do that. Somehow pizza never gets old.
Problem solving is at 10.
Oh, 12, yeah, 12 every Saturday there'll be a problem solving. By the way, the calendar is already on the website for this class, and the TA hours are already posted, and so on. There's TA hours every single day, so you get TA help anytime you want, literally. So solve lots and lots of problems, and they won't be formally graded, the problem sets, but we will have a few homeworks. Not too onerous and not too many, but they will come straight from the problem sets. So if you remember in 6161, the algorithms course, we didn't have regular homeworks, but here, say every 3 weeks or so, we'll have a homework assignment due, and just to keep you solving problems and making sure you don't fall too much behind, and that you don't get this crazy idea to procrastinate and only work on things, you know, right before an exam or right before the class is over, which is not a good thing. You know, you don't become a MacGyver overnight, right? You have to work at it long and hard and consistently over a long period of time, and you already know how I feel about these things if you remember my algorithms course. And of course, there'll be extra credit opportunities, lots of them, and you know, you can do that for fun and profit, and brainstorm and work in groups, and weekend problem-solving sessions. It's all good. And for submissions, this semester we have new technology for submission. Keshav and others have created a wonderful Google web form where you kind of submit your extra credit and weekly readings into this web form. And it does all the right things, and has menus, and it's beautiful, it works, it's nice, it'll save you and us a lot of time and trouble. So there's a link to that from the class website, and so no more email submission, just a Google form submission. Class structure, attendance, again, I want to reward you just for showing up, so 10% for just being here. There'll be homeworks worth about 20%, readings 20%, midterm and final, about a quarter each, and of course lots of extra credit opportunities. And the best strategy you already know is solve lots of problems, not a mystery. Work in groups, it's all good. All right. You know, I'm sorry I even have to say this, but you know, last semester and last year in general, and mostly in the undergraduate course, we had a lot of instances of cheating. The short story is don't do it. You know, you can use web resources to brainstorm. Of course, you should try to solve problems on your own really hard before you even look stuff on the web. But it's okay to look on the web, but it's not okay to copy stuff from the web onto your homework solutions or onto your exam. Again, I'm almost apologetic for having to say that out loud. It's so obvious, but still, last year we had a number of cases where people copied stuff, and we had to call them in and had some tough conversations or awkward conversations with some of them. So examples of cheating is copying solutions directly from other people or the web. cutting and pasting from web sources or websites. Now websites that basically, their business model is computer-aided plagiarism, or computer-aided cheating. They make money off of that. People sign up and post answers, and people post solutions, and that's not cool to do. That breaks the UVA honor code. That's cheating, that's plagiarism, don't do it. We instituted this rule, this very, very helpful litmus test. That's why I have it in red here. Don't submit answers that you don't understand. If you submit an answer in an exam or in a homework that you don't understand what you wrote, that's very suspicious. And it's very obvious to the TAs that this happens, because sometimes people copy stuff on the web, including the errors that they found on the web, and they don't even know it's full of mistakes because they don't understand enough to even tell that it's wrong, but they copy it anyway with the errors, and that's doubly embarrassing for the student that we have to call in, one for copying, two for copying something wrong. And just so you know how convoluted it gets, some people deliberately post on the web wrong answers for other people to copy, knowing that they'll look for them and find them using Google. So they deliberately sabotage each other. That's pretty Machiavellian. That's pretty convoluted. Just so you know, this happens. And if you're a TA for another class, how many here are TAs? So you should know this happens. So when you look at your students' answer when you do grading, keep that in mind. And by the way, this is not an exhaustive list of all ways to cheat. So, and cramming is, I really don't like cramming and procrastinating, because that exacerbates the urgency and the panic to cheat later on when everything comes to a head at the end of the semester and you didn't study enough and you crammed and you procrastinated. That kind of puts on extra pressure to cut corners and possibly cheat. So I'll do everything I can to help you not cram in this class by having weekly readings and occasional homework and so on, so you stay on top of things. And so overall, let's keep things positive. Let's brainstorm a lot, collaborate, but not play gotcha with each other. And because when students try to play gotcha with a professor, the professor can play gotcha right back. And guess what? Professors can play gotcha better than students, and we have all the resources of the university behind us. So including plagiarism detection tools that are automated, all sorts of things. So again, if your TAs convey that sentiment to your students, let's try to clamp down on inappropriate behavior. Is counterproductive to learning and teaching. Okay, so enough of that. My contact information and the readings. Again, there's be a large category of readings. Those who took my course before, it's the same list as before, but try to focus on things that you haven't done before, right? So if you already read certain books or papers from this long list, try to read other books and other papers, and it's okay to submit some reviews from before if you insist, but you'll get more out of reading extra stuff. So some things are required, like the 7 Habits of Highly Effective People and so on. If you read that before, that's okay. You can use that review from before, or maybe reread some sections, or read sections that you haven't read before because maybe you haven't read the whole thing before. So do the sensible thing. I mean, we're all graduate students here and interested in learning and research and thinking and brainstorming and problem solving. So do the right things. And there's still a lot of electives on this list that you can focus on. And one of my favorites is time management. Right? How many of you have seen that talk from before? Okay, good. Now this talk is so good that I think I personally watch it every year again. Just for my personal edification, it's so useful. So again, I don't want you to repeat unnecessary work, but some things are worth repeating. They're so good. Now this is one of the videos I think I showed you in algorithms, right? The scale of the universe. It's always fun to watch again, but this is true to size objects. This is the scale in meters. So this is like 1 millimeter. So you have mites, and you have a single cell, bacteria and dust particles and water droplets, and all the way down to chromosomes and bacterias and DNA molecules. Eventually you get down to individual transistors, which are roughly 10⁻⁷, right? 1/10 millionths of a meter, and even smaller things still. Here's a DNA molecule, same relative size to the other objects shown. Buckyball molecules, right? So the reason I'm showing this kind of things to students is to keep your mind wrapped very tightly around orders of magnitude and scale of things. And computer science is all about scalability and scale. And if orders of magnitude get away from you and you're not sure what 2 to the 30 is, it's always good to refresh your recalibrate your ability to deal with scale. And what is 2 to the 30 now? We mentioned it. Quick, 2 to the 30 is equal to what? It's too late already. All right, so now do it slowly. What is 2 to the 30? It's about 1 billion, right? Because 2 to the 10 is about 1 million. I mean, excuse me, 2 to the 10 is about 1,000, and 2 to the 10 cubed is 1,000, 1,000, 1,000, which is 1 billion. But anyway, this kind of scale should come very naturally to you as computer scientists. If you have Moore's law, it's all about exponentials and exponential growth. Here now we fast zoom back out, we're all the way down to quarks, right? And then when we zoom back out, and here's the ant again, and there's a bird, and there's a human being about 2 meters, and now we're the meter scale again. There are crabs that are bigger than humans, by the way. That was news to me. I wouldn't want to meet one of those underwater. There's a whale, sequoia trees, redwoods, there's a jumbo jet. Titanic was about this size relative to the pyramids, Hoover Dam. Now we're 10 to the 3, which is 1 kilometer scale. At that scale, you have some Central Park and tall buildings, and now we're at 10 to the 5th, right? We have about 100 kilometer scale. We have islands, entire states, countries, and small moons of the solar system. And by the way, on the web, this is an interactive app. You can also get it through your iPhone. It's pretty fascinating to watch. Also, a lot of these things, when you click on them, you can get more information. Here's Minecraft world right here. That's about as big as Neptune, right? That's bigger than I would have guessed. Distance from Earth to the moon right here. Here's the sun. And there are stars that are so big that if you put those stars where the sun is in our solar system, the Earth will be inside them. In fact, Mars will be inside them because they're so big. So the sun is now disappeared into this little dot, and look at the size of these stars in relative size perspective. They're millions of times bigger in diameter than the sun. So this is the distance of Neptune to the Earth, and some stars are bigger than that. Here's one light day, right, that distance there. And here you get some nebula and small galaxies and so on. Again, this is just a fascinating, quick calibration. This is 1 light year across right here. It's a great calibration of sizes, relative sizes of things in the universe. From the very, very small, all the way down to the Planck length, all the way up to the very, very large entire galaxies, the great attractor, and very, very large scale objects. The total size is like roughly 50 orders of magnitude, 10 to the 50, from the very, very small to the very, very large. We're sort of right in the middle of that. Human scale right here of 1 meter or 2, a few meters size rooms and building. That's right in the middle of this very small to very large, interesting. It's right, just almost exactly right down the middle. So there's a whole universe below us as there is above us in terms of scale and size. There are some galaxies. Some galaxies are much bigger than the Milky Way. So much bigger, in fact, that they're thousands of times bigger. Right? And we got then clusters of galaxies, and soon enough it peters out as the entire known universe. Right? That's we're almost there now. 1 gigaparsec, several billion light years, and that's about it as far as we know. 10 to the 27 meters. Then we're back down. So something like this is kind of an interesting exercise to look at least once every 6 months or a year. It just takes a few minutes and helps you wrap your mind very tightly around scales and relative orders of magnitude. All right, so you know what's in the required readings. The required readings are in red. The rest are also listed there, and I won't harp on it. I also give extra credit for movies. So if you've seen the Imitation Game, that's fine. The Martian, that's also another good one. Again, if you've seen them, don't have to rewatch them. Just give it a review, and you're good for that. stick it into that form on the Google Web document, and we're good at that. As far as notation, there's a handout called Basic Concepts in Notation. It's on the class website. It's right on the class homepage. And if you ever have questions about definitions, always go back to this document, go through it, and it defines about 10 or a dozen pages, and it defines most of the concepts, terms, and definitions in this course about languages and strings and types of infinities and diagonalization and dovetailing and one-to-one correspondences and onto functions and so on. And it's one place, one-stop shopping for all terms and definitions. It's a very nice resource. So refer to that often and early. One of my favorite cartoons, we talk about definitions, make sure you understand what the words mean. In this class, most of you will make type errors. You won't even remember or know in specific moments what the type of the object is, never mind its value, right? Because if you don't know if it's a mammal or not, you don't know if it's a zebra, right? So types of objects and definitions are very, very important in this class, even more so than other classes. So when Johannes Kepler was telling to his colleagues, so you see the orbit of a planet is elliptical, he was taking for granted that they don't know what's an orbit, they don't know what's a planet, they don't know what's elliptical, because I never heard about such things. So always go back to definitions if you're not sure what things are. And if you think you know what things mean, make sure, just review and doubly make sure that you're good at the definitions. Another interesting resource is discrete math review slides that talk about sets, unions, intersections, infinite sets, cardinalities, function types, lots of different topics here. This goes on, this is just the first few slides. Again, a very nice review of discrete math. Yeah.
Just a quick question on this. I had a problem printing it out last semester. I was wondering it's a large format. Is there a specific way you're supposed to handle this document?
I can arrange for a kind of a 4x4 kind of a format. Instead of full page, I can make it 4 slides per page. Is that what you're talking about?
Yeah, I was just wondering if it was designed to be like viewed a certain way.
Well, so it was designed to be like in a slide format for overhead slides. Basically. Okay. And this is from the old days when we had these slide projectors with transparency. So this is like old school. That kind of tells you how old I am. When I was using overhead transparencies, probably most of you haven't been alive yet. So, but now I'm dating myself. So, yeah, that's why it's kind of large format. But it's also nice because it's kind of spaced out and you can take notes on it, you can print a hard copy and that kind of thing. So it has advantages for having it in large format.
I was just wondering.
Yeah, the small format one is this other document that I showed you earlier. That probably overlaps with this slide set by probably 50%. It's just more like prose here in terms of paragraphs. But here it's more like in slide presentation format. So actually, for those of you who are TAs that are trying to explain discrete math concepts, to students, or even just review discrete math in some programming class, you can actually use these as slides. You can use this PDF and just project them, one slide after another for your students or your colleagues, and that's a nice presentation of certain concepts, basic concepts of discrete mathematics. All right. So again, the book How to Solve It by Polya, very, very important. And please read this book, Infinity and the Mind. How many have read this book before, Infinity and the Mind? All right, in this course, that's required reading. So I know you've seen How to Solve It by Polya before, because that was part of the algorithms course as well. This is new, at least to those who take an algorithms degree. Gödel Escher Bach is always a good read, and I highly recommend these other 2 books, and I think I mentioned them in the algorithms course as well. Even How to the World. How to not believe stuff just because somebody said so, using analytical thinking, your own rationality, and putting everything to the test of scientific method, and whether it holds water or makes sense or is inconsistent with other things. Really good book for that by Carl Sagan. And of course, a fun read is The What If by the author of XKCD, the cartoonist. That's always nice. So I want at least 2 submissions per week. And they're due 11:59 Monday, and there'll be no late credit for that. If you miss that deadline on a Monday, that's it for the 2 submissions. even in the algorithms course last semester, a bunch of people procrastinated in the last 48 hours of the course to try to submit 20 or 30 or 40 things. That's just not credible, sorry. And that goes against the spirit of what I'm trying to coach you on, and that is, problem solving and slowly pacing yourself over time and rewinding your brain to think more rationally and incisively and analytically, and you can't do it in 2 days. It's like saying I'm going to run the Boston Marathon, and I've never ran before, but I practiced the previous weekend, and now I'm a good runner. No, you're not. You'll probably have a medical emergency if you try to do that. Don't do that. So at least 2 per week, and at most 2 per day. So now this rule is new. So you can't submit 20 things in 1 day, or even 5 things in 1 day. 2 per day. That means if you want a lot of extra credit, you got to submit it, pace it over a long period of time, not in the last 48 hours of the course. Okay, so we will strictly enforce this. If you submit 3 per day, you only get credit for 2, and the third doesn't spill over. So don't submit more than 2 per day. We have spreadsheets that automatically, using formulas, enforce this rule. It's not even us, it's Google enforces this rule for us now based on web forms, thanks to Kashav and others who implemented that. Right? That's great. So again, I'm trying to help you to avoid cramming and avoid procrastination. That's a very important skill, in everything you do in life. So that too will be assisted and encouraged and helped you with in this course. Okay. And you don't have to write much, 1 or 2 paragraphs per article, a couple of pages per book. It's not very onerous, and there's no way to get it wrong, right? As you know, it's your opinions that you're writing. There's nothing I can tell you is shouldn't be your opinion. So please do the right things. Don't procrastinate. Submit things on time, and then it'll be cool. So there's a wide variety of subjects, as you know, about biological computing, about quantum computing. So here's a chance to learn yet more things on top of what you learned last semester by reading all sorts of stuff that you may have skipped or didn't get to last semester. Just keep building on that in terms of reading and cool ideas and extra credit, kind of readings and studies of different fields and so on. Cool ideas from all over the place. And of course, there's various links to websites and Wikipedia articles, and there's plenty of stuff that I'm sure each and every one of you did not get to last semester, even if you took my course already. There's plenty of new opportunities for learning and cool ideas. All right, so as far as advice, we already mentioned before, we said working groups, don't fall behind, don't cram, it won't even work. You get credit for being here, so attend every lecture. And by the way, it's a long lecture. It's kind of an experimental way that instead of having two meetings per week, 1.25 hours each, we're going to have 1 meeting every Tuesday, and that's going to be 2.5 hours. And we'll probably take a break in the middle sometime after an hour and a half or so, and we'll take a 10-minute break, get some water, go to the restroom, whatever, and then we'll continue for another hour. So it's a 2.5-hour meeting, but only once a week. We'll see how it goes. And we'll see if my voice even holds out for 2.5 hours. I think it will, but if not, we'll have maybe Kashav finish the lecture for me. And the key is to solve lots of problems. And in this course, even more than algorithms, there'll be lots and lots of interesting problems, a lot of opportunities for brainstorming and working in groups. It's really cool stuff. So the goal is to become a better problem solving like MacGyver. Of course, nowadays we got Matt Damon on Mars, surviving for a couple of years on Mars with only a sack of potatoes. That's pretty good. And centrifuge problem, if remember that, we'll just go over it quickly. You can balance 5 test tubes by merging 2 solutions. You merge a solution for 2, which is obviously balanced, with a solution for 3, which is also balanced, and together you merge them into a solution for 5, and it's a principle of superposition, right? And you can superpose these 2 solutions, and this solution will also be balanced as 5 test tubes. Right? Any questions about that? Notice the properties of the solution are even more important than the solution itself, because it doesn't use any trigonometry. It generalizes, so from 5 to 7, by flipping the holes and the non-holes, you can get the complementary solution, right? And didn't use vectors, didn't use equations. You could have used trigonometry and vectors and sines and cosines, you could have. But if you didn't, that's even better, because you don't have to worry about sines and cosines, and you can also explain the solution to somebody on the street, and they'll understand and believe it. And importantly, there's no place for truth to hide here. You know, it's obvious that this is a solution. You can verify this empirically. I actually have a fidget spinner that nicely exhibits this. I forgot to bring it, but I'll bring it next time if I remember. So this actually works. And it's important to understand the general principles that work here. Superposition and complementarity. If you have a solution, the negation of that is also a solution, necessarily, because holes are nothing but negative masses, mathematically speaking. So when you're balancing a bunch of positive masses, or the complementary negative masses, which are the holes, it's equivalent. So that's why every solution has a complementary solution, necessarily. There's no way to avoid that. And between now and you've seen this, you can easily solve much bigger problems. Like if you have a centrifuge with 360 holes, can you spin up 5? I'm going to say yes. 7? I'm going to say yes. I'm going to say you can spin up 7 test tubes in a 360 hole centrifuge. Yes, you can. 11? Yeah, why 11? 4 plus 7. Well, why can't you do 11 here? Not 12 holes.
There's one which is not that.
Because if 11 is possible, 1 must be possible, but 1 isn't possible because that's way off kilter. But 11 is 7 plus 4, so where's the logic go wrong? We said you can superpose solutions, so 11 is just 7 plus 4, or it's 5 plus 2 plus 2 plus 2. Okay. So you have geometric constraints that begin to matter. Yeah, you can compose solutions like this, merge them, but when you start merging enough and fewer holes remain, there's less freedom to fill in the other holes with the newly merged solutions, and you can begin to have collisions. Geometric constraints begin to dominate after a while. But you can see that from the 360-degree centrifuge, most of the numbers are doable. How many can see that? Because you can do 2 and 2 and 2 and 2, so all the even numbers are doable. How many can see that? All the even ones are doable. There's pairs of 2s. Now, if you start with a 3 and then add 2s, then most of the odd numbers are doable too. How many can see that? 1 is not doable, and 359 is not doable too, because that's the complement of 1. But most of the others are doable. So you see, this also generalizes. Once you have these insights, as opposed to just having a point solution with sines and cosines that only works for 5, with these general principles, you can generalize it to many other situations. So it has kind of a high elegance kind of value, and this is kind of problem solving at its best. And I think I've told you in algorithms, I don't know if I showed this in algorithms, but if I didn't, I should have. In this course especially, don't use induction unless you absolutely have to, and you almost never have to, right? So, you know, adding up numbers from 1 to 100, you can do it by writing them backwards, and then you have 101 in each column sum, right? Did I show you some algorithms by there? I don't know. Yeah, so I'm glad I did. And once you add up these 101s, there's 100 of them, and the answer is only half of that because you've added it twice. Right? Carl Friedrich Gauss famously did this when he was a 7-year-old kindergarten child, and that's pretty good for a 7-year-old. Actually, it's pretty good for anybody to be able to do this quickly. And you can do it geometrically by looking at the staircase, and on the staircase, you can double it up. The area of the staircase is exactly the sum of integers, 1 plus 2 units of area plus 3 plus 4 all the way up to n. Double up the staircase, flip it over, put it on top of the original staircase, and basically you have a rectangle now that's n by n plus 1, and so the answer is just the product of n and n plus 1, but divided by 2 because you've added it twice, once in the red and once in the blue. So that's a very nice feature of this kind of proofs by pictures or proof by kind of intuitive arguments. It sheds a lot of light on truth and tells you why something is true. And by the way, this also shows you why the formula has to look like this, right? So the formula must be a quadratic because it's an area, right, proportional to n on the side. So it's not going to be a cubic. It's not going to be an n log n. It's not going to be an n times n square root of n. It's not going to be an n cubed. It's got to be quadratic. And on the bottom, it has to be a factor of 2. It's not going to be 3 or 7 or pi or e or anything else because you're adding 2 areas, so you got to divide the 2 out because you're taking twice as much as you had to. So one day, 20 years from now, when you're in some cocktail party and somebody says, you know, quick, what's the sum of integers? if you think about the staircase, and you will remember the staircase, you won't remember an induction proof that's 3 pages long, but the staircase you will remember, and the formula comes right out of this, falls right out of the staircase picture like this. The denominator has to be 2, the top has to be a quadratic, and one of the sides is off by 1, because no matter how you stack these two, one of the 2 sides will be larger than the other by 1 unit. That's the +1 here. So this tells you exactly what the formula is in 20 years. You won't have to remember the formula. You just derive it quickly in your head from remembering the staircase. That's a lot of value for a proof, right? And this generalizes to higher dimensions and lots of other scenarios. So again, this is worth repeating. The drawbacks of induction is that you have to have a priority. You have to have a priori knowledge of the formula before you even start proving anything. You're gonna know what the formula is. That's a drawback. Because sometimes you don't know what the formula is. The induction doesn't give you the formula, but this staircase picture does give you the formula. And it's easy to make mistakes in induction. It's long, it's tedious, it's very mechanical, it's pedantic. It's hard to write down, it's tedious, it's hard to grade when you look at this. Try to grade an inductive proof that's 3 pages long, full of dozens of lines of algebra. Good luck to you with writing it down, and good luck to you with trying to grade it. And it doesn't shed a lot of light on truth. It's hard to check. It's hard to convince somebody that it's true. A person off the street is not going to understand what you're talking about. When you show them an inductive proof of a staircase, they will get it quickly. And even children will understand the staircase proof, but they'll have no idea if you try to push induction on them. And induction is not very convincing. It's just correct. Correct is not good enough anymore. Right? Don't get me wrong. Being correct is better than being incorrect. Let's make sure we get that straight. But once you're correct, it's better to be insightful and elegant and generalizable and wise on top of being correct. And in this course, just like in the algorithms course, we'll strive for that kind of ethos as we solve these problems, right? And induction is kind of obfuscates connections and doesn't generalize, and it has lots of problems. So, if you need to solve a problem and it's kind of annoying and not obvious, still, don't do this as a first resort. Instead, try to be more elegant, more insightful, more incisive. It's better. So only use induction as a last resort. So I'm here to tell you induction, just say no. Now, having said that, what I'm not saying is that induction never has a use and should never be used. I'm not saying that. I'm just saying don't use it until you absolutely have to. And in this course, you almost never have to use induction. In fact, any problem that I give you, induction will never be the only way to solve it. Now, don't get me wrong, you can use induction all sorts of ways to solve problems, even in this course, but I'm asking you not to. I'm asking you to look for other ways to solve it that are much more incisive, insightful, wise, generalizable, and ways that shed light on truth rather than just pedantically turning a crank and then raising your hands and walking away in victory as if you won the lottery. Don't do that. So induction is like a nuclear weapon. It may be okay to have one, but you should almost never ever use it unless absolutely necessary, and it's almost never absolutely necessary. So it's heavy artillery. Any questions about that? Now, I know some professors run half their course on theory using induction. That's their option. That's their decision. I'd rather not. And I think you'll be better off if you don't either. Okay, so simple generalization of this staircase thing to other problems. So sum of a quarter is a quarter plus a quarter squared plus a quarter cubed plus a quarter to the fourth. Sum of powers of a quarter. What's the answer? It goes out all the way to infinity. What's the sum? Anyone want to take a guess? Remember maybe if you said it before? 1/3. 1/3, yeah. How many agree 1/3? Only one person, 2 people agree with you. Okay. What if we use this picture? So here's a quarter of the 1 by 1 square. So that's a quarter. That's a quarter of a quarter. That's a quarter squared. That's a quarter of a quarter of a quarter, quarter cubed. So the area of the red squares is the sum. How many can see that? Okay. And what's the area of the red squares? It's not so obvious until we have the red complemented with the blue. So the blue squares are exactly the same as the red squares, complete copy, just vertical instead of horizontal. And the remaining black squares are also the same as the blue or the red, and together they fill out the entire square. So how many can see a third now? Good. End of story. You could have used induction, you could have used some formula, you could have used some calculus even to prove this, but not necessary. The picture just tells you the truth very, very obviously. It has no choice but to be a third. It's not going to be a quarter, it's not going to be a fifth. It can't, because they all three of them have to share the square. And there's three of them, and they're completely not overlapping. They share the square between them, so each one gets a third. That's pretty obvious. So this picture sheds light on truth. Now, if you use a formula, you still get a third. But you won't understand why it's a third, not a quarter or a fifth. Any questions about that? About that ethos in problem solving? Elegance, finesse, panache. What does it say in French? Panache. Okay, and this generalizes. So if you want powers of an eighth, same thing happens, except in 3D. Right, so now you have cubes filling up in 1 by 1 by 1 cube, and there's 1/8 of the cube, and there's 1/8 of the remaining eighth, and so on. So all the yellow ones are powers of an eighth all the way out. And how many of them are all together? How many of these colored series are there total in this cube, filling up completely the bottom of the cube? 7. So the total answer to this? 1/7. You see how obvious, how the answers not just fall into your lap from these generalizations. And now you can solve the same problem in 4 dimensions. If you have a tesseract, what would be the series for the tesseract picture? 1/16, powers of 16. What would be the answer for the sum of all these powers of 1/16? 1/50. End of story. You don't need a fancy formula, you don't need induction. Now you're going to higher dimensions. You see, there's value in this kind of thinking and inference and problem solving. And you can also get furniture that look like this, by the way. If your loved ones, this makes a great Christmas gift if your loved ones appreciate, power series and proof by pictures. So, any questions about any of that? So this is the kind of ethos we will use in solving problems in this course, and we get a lot of mileage out of that. So, powers of, sum of cubes. So these are now extra credit problems. I'm just going to throw at you in quick succession. Powers of cubes. Tell me what it is for adding up 1 through n cubed. Again, try to use a picture kind of proof, an intuitive, generalizable kind of picture proof. Prove that the square root of 2 is irrational. The Greeks knew that, and try to do that too. Again, each one of these proofs is just either a picture or a few sentences, a paragraph at most. Never, and don't use induction on any of these. Prove it as an infinity of primes. Again, something that was known to the ancient Greeks. Prove it as arbitrarily long consecutive composite integer blocks. In other words, there's arbitrarily long consecutive blocks of integers containing no primes. They're called the prime deserts. And there's ones of arbitrarily long length. Not infinite length, because otherwise there wouldn't be an infinity of primes.
Would you call it the prime?
Prime deserts.
Desert?
Desert, yeah, like a desert, a sand desert without water. So this is a prime desert without primes, with only composites there. But not a prime to be seen in these deserts of integers. Are the complex numbers closed under exponentiation? They're certainly closed under multiplication, the complex numbers, a plus bi. But are they closed under exponentiation? That's not obvious. And if so, what is the value of I to the I? Right? So again, these are just some extra credit problems for extra practice with rationality and logic, inference, and elegant proofs. Does exponentiation preserve the rationality? So exponentiation doesn't preserve rationality. If you have a set of rational numbers, you take 2 numbers, exponentiate them, and the answer will not necessarily be rational. Could you prove to me that the set of rational numbers is not closed under exponentiation? How would you prove that?
The previous one. The previous one, I to the I.
Well, but let's say irrational real numbers. Let's stay away from the complexes on this one. But you're right. But let's stay away from the complexes. Let's say our 2 rational numbers. So I'm asking a slightly different question. Are 2 rational numbers exponentiated? Can the answer be irrational? How many say yes? How many say no? Well, there's only one person voting. All right, I'll ask again. Is it true that if you take two rational numbers and exponentiate them one to the other, to the power of the other, the answer could somehow be irrational? Let me back up. What's an irrational number? Remember I said understand definitions. What's the definition of an irrational number?
It doesn't have the number of decimals after the comma doesn't have.
Okay, so that number of decimals after the comma doesn't end. How many agree with that? All right. So 0.333333 never ends. Is that irrational then? Ah, okay. So what's the definition of an irrational number?
It has to be written as a fraction.
Can be written as a fraction. So you have to be careful when we start talking about notation. Expression in a certain notation, because if it doesn't end, it can be still a third, or a seventh, or something else. Okay, it can be written as a fraction. So can you give me an example of two rational numbers when you exponentiate one to the other, cannot be expressed, the result, as another fraction? Yeah, 2 to the 1/2, for example. What's 2 to the 1/2? Square root of 2. Square root of 2 is not rational. That's one of the previous problems you need to prove. It's not obvious. But this question is not even that. This question is, does the irrational real numbers set, is that closed under exponentiation? Can you have an irrational raised to an irrational and all of a sudden get a rational number back? Is that possible?
Yes.
Yes.
So prove or disprove that. That's the question. All right. This one, again, if you see in the algorithms course, that's all right. But x to the x to the x to the x all the way out is equal to 2, one variable, one unknown, solve for x. And the answer is unique, interestingly enough. A ladder of resistances, each one is, say, R ohms in resistance, and they're arranged like this, like an infinite ladder. It goes all the way out to infinity in this direction. The question is, what is the resistance between points x and y here? If you took an ohm meter and measured it, you can actually do this experiment. You won't have an infinite ladder, you have a very long ladder, and the answer will converge after a while on some fixed value. Did I mention that in the algorithms course? Okay. I haven't? No. How many have seen this problem before? All right, only one person. All right.
But not in the algorithm.
All right, so there it is. Interesting problem. And by the way, this problem will relate to the material of this course very directly. Many of them will actually, and we'll get to that later when we talk about solutions to these things. So the next component of the course will be about a long historical timeline going back to Aristotle and ancient Greeks and how we got to this point, how we got from abacus to iPhone, over a 2,300-year period. And it's a very interesting journey. And the reason we do this is because knowing the big picture is very, very informative, right? Science builds heavily on previous accomplishments and ideas and thoughts, and so does mathematics and everything else that we do. And often the simplest ideas have the biggest impact, and they're the most subtle and fundamental and important. And the fundamental progress, the big leaps, were done few and far between by only a few individuals. A few hundred individuals throughout history that provided 95% of the value of where we are today, which is kind of interesting. Newton was one of them. Euclid was another. Gauss was a third. Turing, no need to even debate that, right? So the field of computer science, as we know, it has many so-called parents, many fathers or parents in general, and it's also inspiring to see how other people approached invention and discovery and how they achieved their monumental things that they came up with. And it shows us what's possible, also it's fun to think about and so on. So it's always cool and interesting and important and fun to kind of stand on the shoulders of giants and see where we were in the past and how we got here. This will help us chart the way forward in the future. As it's always a nice guideline or a roadmap to look forward, is to understand how we got to this place to begin with. So we'll discuss the accomplishments of a lot of these luminaries throughout history, beginning with Aristotle and Euclid, Archimedes, and I highlighted a few in red that are even more relevant than some of the others to computer science theory and computer science in general. Really, the giants of advanced thinking and kind of out of the box kind of ideas and generating techniques of which we continue to build on to this day, and will continue for many centuries to come. And here are some more. We'll talk about Cantor more specifically. In fact, I think I'll talk about Cantor more today because the first homework assignment is already posted to the website. Already talks about infinities and cardinalities. And I want you to understand more about it before spending too much time on these other ones. And then we'll go back and so we won't necessarily cover this in a linear progression throughout time. We'll jump around. But we'll cover most of it before we're done. So here are some of the luminaries of mathematics and science and the great thinkers of going back to ancient times. And of course, there's Newton and Gauss and Archimedes and Euler and all these other people that I kind of list down on the side. Each one is represented by some equation or some object that they pioneered or some technique, just representative of their contributions. But now let's jump directly to Cantor before we continue with the others. So this takes us to the 1800s, late 1800s, and Georg Cantor basically pioneered modern set theory. Him and John Venn. And at the time, he started exploring the notion of infinities and relative magnitudes of infinity, and he said that some infinities are bigger than others, and people doubted that and didn't take his ideas seriously. And also infinity at the time was considered associated with the divine, and so questioning infinities and comparing them to one another and debating about them was considered almost sacrilegious or heresy. And so his work was kind of shunned, and he had trouble getting published and getting traction for his ideas. Now we know that ideas were brilliant. Turing pioneered computer science on top of the ideas of Cantor, specifically about the ideas of diagonalization and one-to-one correspondences with infinite sets. But at the time, he had some trouble towards the end of his days. He became depressed, ended up in an insane asylum, and soon you'll see why when we talk about diagonalization and one-to-one correspondences, the relative magnitudes of infinities, and the fact that not all infinities are created equal. Some infinities are bigger than other infinities, it turns out. And we're about to prove that in the next 20 minutes. But one person that did understand the grandeur of these ideas and the usefulness of them was David Hilbert, and he popularized the ideas of Cantor. He also formulated some hypotheses, like the continuum hypothesis. It's a conjecture that wasn't settled until 100 years later, in the 1960s, and he created or defined certain sets that nobody ever thought of before because they had such strange convoluted properties, and we'll see some examples of that. Right, so he laid the foundation for all computer science theory. The work of Gödel, the work of Turing, the work of Church, all built on top of this guy. Okay, and there's now hundreds of books about his work and about transfinite arithmetic. And one really, really good book is Infinity and the Mind by Rucker, and I want you to read this. This is required reading for this course. It's a short book, it's a paperback, not very technical, easy to read. You probably knock it off in a weekend. But really, will really open your mind, blow your mind on a number of levels with respect to these esoteric concepts, which we'll start talking about today in the next hour. Okay, so this guy gets a lot of cred, a lot of street cred for his thoughts and contributions and the novelty of his ideas. And in terms of the textbook, on page 176, 174, it's talking about one-to-one correspondences, dovetailing, diagonalization. This is all due to Cantor. And we're about to go into this stuff in greater detail right now. I'm just showing you the book where you can read about it specifically. And of course, there's wiki pages and lots of other sources where you can read about it. So, diving into this, let's say you have an infinite hotel, infinite number of rooms. All the rooms are occupied. There's a guest in every room. The rooms are numbered 1, 2, 3, 4, 5, all the way out. And you have another guest coming in the lobby wanting a room, right? You're the hotel manager. What do you do to accommodate the guest? So that's one of the puzzles put forth by Georg Cantor, late 1800s. So what do you do? Where do you put this new guests into the infinite hotel. All the rooms are occupied currently. Anybody else? In case you said it too quiet.
You can ask each guest to move to the next room.
Yeah, you can ask each guest to move to the next room, and if you do that, guest number 1 goes to room number 2, 2 goes to room number 3, guest number 3 goes to room number 4, and everybody goes one down. So the formula is f of n is equal to n plus 1. That's the mapping. And the new guest now goes into unoccupied room number 1. End of story. So you accommodate one new guest in the hotel, even though all the rooms were occupied before, and everybody still has a room. Any questions or comments about that? That's a cool trick. You can only do this with infinite sets. For finite sets, this won't work. So even the MGM Grand in Las Vegas, 6,000 rooms, they can't pull this trick. Not if all the rooms are occupied. Now we're going to up the ante. Let's say it's not just one guest wanting a room, it's an infinite number of guests all waiting in the lobby. It's a big lobby. Business is good. And all these guests want rooms. What do you do now? Let's first see what you shouldn't do. Why shouldn't you pull this trick with a single guest over and over and over and over again for all the other guests in the line? It never stops. Obviously, it will not stop. But even worse than that, let's say it did stop at some point. Or let's say that we don't mind that it never stops. What's an even worse problem than that? I want you to think even deeper than that. This first guest will get room number 1, but then the next guest behind him, after everybody moves again down the line, will get room number 1. So this first guest will get room number 1, then room number 2, then we'll get room number 3, then room number 4. What's the final room that this guest will end up in? There is no final room. This guest will never get his own permanent room. This guest will not have any fixed room number, which means this guest has no room. How many see that? That's worse than it will never end. Because even if it ended, it would still have no room. Which is kind of weird, right? So you have to think about that concept of infinity very, very incisively. You have to wrap your mind very tightly around that concept in this course, because most of the sets that we'll deal with were infinite sets in this course, and some of them will not even be countable sets, they'll be uncountably infinite sets. We'll get into countability in a minute. Another thing you can't do is you can't say, take this guest and put it in the last room. Why can't you put that guest in the last room? Because he doesn't know where the last room is?
There's no last
Because if there is no last room, it's worse than not knowing where it is. It ain't even there to know where it is. There is no last room. So you can't say, put him in the last room. Well, let's be more precise. You can say it, it just doesn't make sense to say it. Right? Nothing stops you from saying it. You're just talking gibberish at that point. It's like saying, put this guest in room number pi. You can say it, but there is no room number pi. There's room 3 and there's room 4, but not room number pi. Right? So that's stuff you cannot do. All right, so what can you do when there's an infinity of guests? How do you accommodate them without all these problems? If I offered an extra credit point, what do you do? Are you holding out for points? Yeah.
Shift them exponents.
Shift them by 2. So each one goes to twice the room number, right? So 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. And if you do that, all the odd rooms are free now, empty. And that's where all these guys, all these new guests go. They go into all the odd rooms, all the empty rooms by having all the previous guests double up to twice the room number. And the formula is f of n is equal to 2n is the mapping of the old guests. How many see that? Okay, any questions about that? Again, you can't pull this kind of stunt with a finite hotel or finite sets.
So you start beginning, or does it all happen at the same time?
All happen at the same time. You know, get over on the intercom and say, okay, guess, your guess number N, please go to room number 2 and go. And they all do that simultaneously in parallel. And all the odd rooms are freed up. Now the new guests allow me know where to, and all the new guests are in parallel simultaneously go to all the odd rooms. Don't ask me about how the elevators work in this hotel. Yeah.
Oh, why can't I do like powers of 2, like 2 to the power n instead of 2 times n?
Oh, good. So she's saying, what if guest number N went to room number 2 to the N? Will this solution still work? How many say yes? All right. Only 3 people raise their hands. So think about it. She's saying guest number N goes to 2 to the N, not 2N, but 2 to the power of N. And then all these, will that free up all the odd rooms? How many say yes?
Not the odd rooms, but I mean.
Yeah, it will.
Yeah. Well,
Yeah, it's
It will,
not the odd
it will.
rooms, but.
all
they
the
also
odd
have-
rooms will be free.
Yeah.
Is that wrong? No, that's correct. A lot of other rooms will be free too. But that doesn't stop the odd rooms from getting freed up. If everybody goes to 2 to the N, only powers of 2 will be occupied, and those aren't odd. So all the odd rooms will be occupied, and this will still work. But what else would be true after this solution?
You have redundancy.
A lot of extra rooms will be also free, other than the original occupied rooms plus the rooms that are occupied by all the guests in the odd places. That's okay. That solution works. What it doesn't do, it doesn't fill up the hotel precisely with all the rooms occupied and no rooms unoccupied, but we didn't ask for that. So that solution is perfectly valid. Any questions about that? Could you go f of n is equal to n factorial? Sure. Will that free up all the odd rooms? Not necessarily, but there'll be plenty of room for, that's a little more complicated because you have to, you know, say exactly where these are going to go, but there's plenty of rooms empty after that too. What if it's that f of n is equal to 2 to the 2 to the n, double exponential? Will that work? How many say yes? Sure. Okay, so there's lots of ways to do it. It's not unique. Right? All right, let's up the ante even more. See how much fun this is and why Cantor went crazy? Now, not only there's an infinite row of guests, there's an infinite number of infinite rows of guests. So each row is infinite, and there's an infinite number of them, all wanting rooms. Business is booming. Big convention in town. How do you accommodate them now? Could you do the one infinite row using this technique, and then do the second row, and then the third row separately, and the fourth row? Why can't you do that? It'll never stop. And some guests will not have rooms, worse than not stopping, because some guests will keep moving and moving and moving, and it'll never end. So no, that won't do. So what can you do? Dovetailing. So what does he mean? Somebody else, what does he mean by dovetailing? That's correct. Now I'm filling the gaps. By the way, it's always good to answer a question in 1 word or 2 words or 1 phrase, because that means you hone in on a fundamental underlying principle that's at work here. Now filling in the gaps is not trivial either, but that 1 or 2 words, that's a pivot, the key everything hinges on is the most important thing. It also forces you to figure out what's the most important idea, and not just throw a lot of words around and hoping some word will stick. It's a shotgun approach, right? Yeah.
Can we order the guests into one line of infinite number of guests and use the previous technique?
Yes, you could. So how would you do that?
For example, we can do first guy in the first line.
All right.
And then second guy in the first line. And the first guy in the second line.
Yeah.
That's exactly right.
Excellent. Good. Perfect harmony between his explanation and the animation. Beautiful. So he's dovetailing through these, right? 10, 11, 12, 13. He's zigzagging among the rows, among the guests, and numbering them in consecutive sequential order in a way that eventually every guest will be numbered by a unique integer. How many see that this will happen? And then take these guesses in this order and use this solution from the previous slide. This solution here. How many see all of that now? Okay. This is called dovetailing, which is what he said originally. And there's lots of other ways to dovetail. This isn't the only way to do it. You can do all sorts of zigzagging techniques, and you could have gone 7 in, and then 6 in this way, and then 5 this way, and 13 that way, and there's lots of ways to do it. You don't have to do it exactly like this. But there's lots of ways that don't work. Right? What if you went down this line all the way out, and then went to the second line and kept numbering that after the end of the first line? What's the problem?
You don't know the.
They would never reach
There's no end.
It'll never end. Why?
There's no end.
Because there is no end. So don't say words as if your words force something onto the universe. The universe is not bound by our words. Right? Just because you utter a sentence, the universe doesn't have to scramble to make your words true. Some people forget that as they go through life. And some of them happen to be in political office, but I digress. Just because you utter words, you throw words around, doesn't imbue meaning on them automatically. And the universe is not bound by what we say. Okay, so you can't go to the end because there is no end, so stop saying stuff like that. Right? Oh no, you could, but you just be talking gibberish. So there's lots of things that could work, but lots of things that will not work either. And there's a famous party song, 99 bottles of beer on the wall, one beer falls down, and there's only 98 bottles of beer on the wall. But there's an infinity of beer bottles on the wall. Aleph naught is the cardinality of the integers, the first countable infinity. Aleph naught bottles of beer on the wall, one falls down, and there's still Aleph naught bottles of beer remaining on the wall because of this hotel business, right? And there's a funny web little video about hotel infinity that kind of plays on these subjects in an amusing way. Extra credit. Okay, so more examples of dovetailing, which is a very, very important technique. We'll get a lot of mileage in this course from the dovetailing technique and also from diagonalization, which is a separate technique that we'll describe in a minute. But we're about to show why there's just as many natural numbers as there are integers, even though the natural numbers are a strict subset of the integers, right? The natural numbers are only the positive integers, and integers include all the negatives too. So how come their cardinalities are the same? How come there's not less natural numbers than there are integers if there's such a small subset? Only roughly half of them, if you will. And here's why. So here are the integers. All the blue ones are the positive ones. All the red ones are the negative ones, right? And we can rearrange them however we like, because the set doesn't have order in it. You can write it in any order you would like. It's still the same set, right? So you can write them in this order, where the positive and the negative ones are interspersed, kind of zipped together. Every odd one is an even, every odd one is positive, every even one is negative. So you can write it in this order, and then you can number this new ordered list with the natural numbers, 1, 2, 3, 4, 5 in green all the way out. So this is a one-to-one correspondence between the integers and the natural numbers. And every natural number is here, and each one is there uniquely. There's no duplicates. Every integer is there, and every integer there is unique without any duplicates. And every natural number has a unique match in the integers and vice versa. So this is a complete one-to-one correspondence between the two sets. And that's why they have the same cardinality, even though one is a strict subset of the other. In fact, a working definition of infinite set is a set that can be put into one-to-one correspondence with a proper subset of itself. Think about that. This is not true for any finite set, and this is always true for every infinite set. So this is one of the definitions of infinity. It's a set that can be put into one-to-one correspondence with a proper subset of itself. Proper means subset, but not equal to the set.
And that's definition of what?
One of the definitions of infinity. In other words, when I say an infinite set, what do I mean by infinite set as opposed to finite set? Well, what I mean is that an infinite set can be put into one-to-one correspondence with a proper subset of itself. It's an if and only if, and it's a definition of infinity. It's a definition of something to be infinite, as opposed to not be infinite, in other words, be finite. Think about it. There's other definitions too, but here we see an example of that. Okay? And therefore, the cardinality of the natural numbers, represented as capital N here, is the same as the cardinality of the integers, represented as a Z. Okay? Any questions about any of this? We're going to go deeper into these concepts. This is just the tip of an iceberg. And another question is, what about the rational numbers, represented by Q? Q stands for quotient, right? So obviously, the natural numbers are a small subset of the rational numbers, right? 7 is a natural number, and 7/1 is a rational number, so 7 is also rational. But 7 1/3 is a rational, but not a natural number. So natural numbers are a small subset of the rational numbers. And obviously, they're not the same set, because 1/3 is in the rationals, but it's not in the natural numbers. So you might be tempted to conclude that the cardinality of the natural numbers are less than the cardinality of the rationals, because it's such a tiny subset of the rationals, right? Every consecutive integers don't have an integer in between, but how many rationals do they have in between any two consecutive integers?
Infinite.
Infinite number. So you think there's so many more fractions than there are whole numbers. Turns out they're the same cardinality, amazingly enough. And here's a proof. It's a proof by dovetailing. And it's a lot like the infinite hotel business, right? So here are all the x's in blue and all the y's in red, and every number in this grid will be a rational number of y over x. So every rational number in the universe that's positive is in this grid as a y over x value. How many can see that? They're all there, right? Now, how do you number them with natural numbers so that creating a one-to-one correspondence between natural numbers and these fractions? So all the fractions are in this grid. Well, one way to do it is dovetail like this, right? In a zigzagging line, just like in this infinite hotel, where you have lots of infinite rows. This is what he was doing earlier, dovetailing between all the rows. And you can do that. Once you do that, this dovetailing, just number them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And that creates a one-to-one correspondence between the greens, which are natural numbers, and these blue-red fractions, which are rational numbers. And every integer, every natural number integer value is in the green, no exceptions, and every rational is in the blue-red fractions. And that shows you that they're exactly one-to-one correspondence, and neither set is bigger than the other. So this kind of way of comparing set sizes generalizes the finite case. If you have 3 cars and 2 drivers, right, and you want to know if there are more cars and more drivers, one way to do it is count the cars, count the drivers, and compare the 2 counts. If you say 3 cars, 2 drivers, okay, 3 is bigger than 2, so there's more cars than drivers. So a set of cars is bigger cardinality than a set of drivers. 3, 2. But that doesn't generalize to infinite sets. In infinite sets, you cannot count the integers and count the fractions. Both are infinite. So you have to generalize the count comparisons in the following. You can ask yourself, is there a way to correspond the drivers to the cars in a way that matches them one-to-one and onto, so that no cars remains without a driver, no driver remains without a car, and nobody doubles up. So you can't assign 2 cars to the same driver. It's one-to-one. So there's no way to do it, no matter how hard you try. You cannot match up 3 things and 2 things in this way, in this one-to-one correspondence manner. If you could, you can conclude that they're the same count. But in this case, you can't. So that works for finite sets to compare cardinalities, and that technique also generalizes to infinite sets. So if you can make a one-to-one correspondence between 2 infinite sets, you can conclude that they have the same cardinality. If you cannot, then you can conclude that one is bigger than the other. Of course, it remains to be seen which one is bigger. That's a separate question. But they're not the same size anymore if you can't do this. Now, showing that you can't do this is actually hard. Harder than showing that you can. Because if you can do this, you only have to show an example. Like in the 3 and the 2, you can show, 3 and the 3, you can show here, that works. Of course, this also works. But this works and I'm done. One example shows I'm done. But if you can't do this with 2 and 3, you have to show that no way will possibly work. And that's a lot of different possibilities. And you want to show that none of them will actually work. And that's a much taller order. It's like proving that you're not a millionaire. That's hard to do. Proving that you're a millionaire is easy. Just show me the money. Show me the cash. Show me the Bitcoin. And you're a millionaire. Okay? But if I want to prove to you that I'm not a millionaire, can I not show you the money, and that's a convincing proof that I'm a millionaire? No. Maybe I'm hiding in an offshore account. Maybe, you know, I have a winning lottery ticket and I haven't cashed yet, and that makes me a millionaire, but you won't know it. Who knows? So keep that in mind. Yeah, question.
Shouldn't we only treat the simplest form of y over x? Because that way aren't we repeating another?
Yeah, so that's a good comment. So he's saying 1 over 1 is the same as 2 over 2 is the same as 3 over 3. They're all equal to 1. So the number 1 is repeated here, here, and here, and same for other things. 3 over 2 is the same as 6 over 4, which is also there up there. So it's saying it's a lot of repetition. So how do you get rid of this repetition? It's not hard to do. Skip them. Very good answer. 2 words. Skip. 1 word. Skip. Skip them. 1.5. Skip them. So yeah, you can do that. So now let's skip them. Right? So when you skip them, just avoid numbering things that were already numbered. So 1, 2, but don't number this. Rather skip that and number the 3, the 4, the 5, but skip that, right? And instead number this one next, and so on. So now we're skipping the duplicates. That was a very good question. So good, I had a slide prepared. I didn't pay him extra to prompt this like that. It's just spontaneous. Okay, any questions about that? So you can even skip duplicate values and not worry about them, and it still works. Okay. So again, this shows that the cardinality of the natural numbers is the same as the cardinality of the fractions, which is mind-blowing. Up until Cantor, the human race didn't realize that. We would only assume that either that they're all infinite, there's no point discussing or debating or analyzing it, or if we were to the point that somebody even questioned it, that would assume that there's many more fractions than naturals. Because between any two consecutive fractions, natural numbers, there's an infinite number of fractions. So how can they be the same quantity if for every integer there's an infinity of fractions? Yeah?
Can you repeat that about the cardinality? Can you say that line again?
Yeah, so the cardinality of the natural numbers is the same as the cardinality of the fractions, of the rational numbers. Q stands for quotient, so the rational numbers, fractions. So we're saying that this is a proof by dovetailing that the two cardinalities are the same. Even though intuitive, it seems that there are many more fractions than there are natural numbers, simply because the natural numbers are a very tiny subset of the fractions. Right? And when Cantor said this and proved it like this, I mean, it was a mind-blowing revelation to the human race. We had no idea. And we're about to see other amazing results on the heels of this one. All right? And you can avoid duplicates. And this is called dovetailing. Right? Now, there's lots of ways of dovetail. We can have dovetail like that, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. We didn't have to do it in this serpentine way. We could have done it like lots of diagonals. How many can see that? That will work too. But that doesn't mean that everything works, right? And here's a way to number them using these diagonals, avoiding duplicates again. But certain things don't work. So let's say you want to number them 1, 2, 3, 4, 5, 6, 7, all the way down the first row. And then later, after the end of the first row, go back to the second row and then the third row and so on. That does not work. That will not yield the one-to-one correspondence. That fails. Why? There is no end to the first row, so you'll never get to the second row, and all these things will be unmatched, and therefore you haven't defined a one-to-one correspondence. You just did some strange thing that didn't yield what you were after. That doesn't mean that the two sets are not the same cardinality. That just means you did not succeed in proving that there are. How many see the difference between these two scenarios? So be careful when you think about these things. Just because you failed to do something doesn't mean that thing is impossible. Okay? That's an important distinction. So some things just don't work. Don't get the idea that any nilly-willy traversal of things is a one-to-one correspondence or a good way to dovetail. It's not. Some things work and some things don't work. Right? Any thoughts about that or questions? All right. So dovetailing, very, very important technique, and we already seen an example of that. This is an example of dovetailing, the naturals and the integers matched up like this. We saw a couple of slides ago. That's an example of dovetailing, where the dovetailing, if you want to show a picture of it, looks like this. The zigzagging is like this, and so 1, 2, 3, 4, 5, 6, 7, 8, just like that. 1, 2, 3, 4, 5, 6. How many see the dovetailing going on here? Whereas before, we didn't quite call it dovetailing, and we didn't show the zigzagging pattern. We just kind of wrote it out like this. Or you can write it out as a function. You can write this as a mathematical function. That's okay too. But I want you to know there's lots of other ways to dovetail. Let me show you a sort of an arithmetic or an algebraic way to dovetail without this picture between the natural numbers and the fractions, the quotients. Right? So we're going to dovetail by writing all fractions whose the maximum of the absolute number of the numerator and the absolute value of the denominator is at most 0, and there's none of them, right? There's no fractions where the maximum of the x and the y is 0 when you have x over y. So we're going to sort the x over y fractions by this key, the max of the absolute value of the x and the absolute value of the y. Now, if you allow the maximum value of the x and the y to be 1, there's only 2 fractions that achieve that constraint, 0 over 1 and 1 over 1. So that's 0 and that's 1. If you allow that maximum value to be 2, you have the first 2, but then you have 1 over 2 and 2 over 1 as well. How many see what's going on here? All right, let's keep going. If you allow it to be 3, you get 1 over 3, 2 over 3, 3 over 1, and 3 over 2. In other words, the maximum value of a numerator and denominator in absolute value will be 3, and then you have new ones popping up, and all the old ones too. So this set keeps increasing, right? And then every line here, when it's 4, when it's 5, there'll be a finite number of new values. How many see there'll be a finite number of additions at every step? I only see 3 hands raising, so I'll repeat the whole thing. All right. We're trying to match the natural numbers to the fractions in a way that doesn't involve some green zigzagging line as a picture, but rather listing them as a list according to this rule. This rule is that the maximum value of the numerator and denominator in absolute value is at most 0. How many fractions satisfy that? 9. How many fractions satisfy that the maximum numerator and denominator value, xy, is at most 1? Well, 2 things, 2 fractions. Right? Then 2 more fractions satisfy when you increase that value to 2, to 3, more fractions, and so on. And when you increase it to 50, there'll be a whole lot more fractions. Okay? And of course, that doesn't even include the negatives. I could have included the negatives here too. I probably should have. Right? Question.
Why is it 2 over 2 included when the max is 2?
Well, when the max is 2, you have 1 over 2 or 2 over 1 or 2 over 2, but 2 over 2 is the same as 1 over 1, and we already have that here. So these are only the new ones added to the previous lines. So I didn't want to have to rewrite the previous line all over again, over and over again. So these are just the new ones. But you're right, each line contains all the previous lines implicitly. The point is that whenever you increase that value, new ones pop up, but only a finite number, right? Other than the ones you already listed. Why? Because the numerator and denominator have to be integers, and they can't be too large of an integer in absolute value, so there's only so many combinations you can have. Roughly, how many combinations do you have total at every level, roughly? If that number is k, roughly how many fractions involving numbers up to k can you have at most? Not a hard question.
K squared?
K squared, roughly. All right, the numerator can be between 0 and k, the denominator can be between 0 and k, so that's up to k squared, and most of them will duplicate, so you can even eliminate them, but the most you can have is k squared. That's a finite number. Now what am I going to do? What am I trying to do? I'm trying to show you a one-to-one correspondence between natural numbers and fractions,
Trying to eliminate.
but without the previous, different proof than the previous one. So once I do that, just number them. 1, 2, 3, 4, 5, 6, 7, 8. So now I've created a dovetailing between, a one-to-one correspondence between natural numbers in red and rational numbers in blue. How many can see that? And I've done that without a green zigzagging line. I've done that algebraically or arithmetically by describing in words and maybe with a couple of equations. the actual correspondence. My point is, you don't have to draw a zigzagging green line to establish a one-to-one correspondence or a dovetailing. This is a form of dovetailing right here. It's just an algebraic or an arithmetic way of describing it rather than a zigzagging green line. How do you understand all this? Yeah, I don't see a huge amount of sea of hands raising there. Ask me questions.
So this is the first class. Can you briefly just remind me what the notations are around max, x, y?
Yeah, so max is the maximum. It's the maximum of these two values. The bars means absolute value, right? So x is a number, absolute value. The bar of x means absolute value of x and absolute value of y. In other words, when x and y are negative, I still want to take the positive values being at most 1. Otherwise, I'll have very large negative values involved. That's why I say absolute value. Otherwise, minus a googol over minus a googolplex will still be on this line because the googol and a googolplex, minus a googolplex are both much less than 2. I don't want that. I want the magnitude, the absolute value, to be less than 2 and 3 and 4 because I want to bound the number of objects on every line. I don't want it to be unbounded. That's why. Any other questions?
Or a comment, but is this similar to the diagonal dovetailing? Because that's saying the sum of the two numerator and the denominator is some number.
It's similar, but it's not exactly the same. This order is not exactly the same as the one in the previous slide. It's similar, but it's not the same thing. Okay? Because I could have written them down here in any order along a particular line, avoiding any similarities with the previous slide on purpose. But it's still a version of dovetailing, and the problem is, the observation is that dovetailing can have many disguises. It can come in many guises, not just a green line in a square grid pattern in a plane. Right? That's my point here. You can describe it in English, you can come up with a formula, you can have some method, or even an algorithm. That will be a perfectly good way to dovetail, but not necessarily having a square with a nice zigzagging green line through it, necessarily. And next, we're about to show that there are more real numbers than rationals. And you might think, the real numbers and the rationals have similar properties. Between any two rationals, how many other rationals are there? Between any two distinct rationals, how many other rationals are there? Not a trick question. Infinite number. Between any two real numbers that are distinct, how many real numbers are there? Infinite number. So you might think that the number of real numbers and cardinality of a set of real numbers and cardinality of a set of the rationals is the same cardinality, because they're both kind of dense. That's false. There are more reals than rationals. And we're about to prove that. But before we prove that, let's take a 10-minute break. Let's come back and say 10 minutes to 7. Guess you want to get some water, go to the restroom. Feel free, and we'll regroup, and then we'll prove this in a few other things.
You can use proof of induction to, you cannot use proof of induction on infinite.
Induction only works on countable finite and there's something called transfinite induction. But that's
The question about more irrational interactions, I was thinking from a weak set point of view. So if you have minus infinity, you always have more irrational interactions. Sorry, you always have more integers than natural numbers. And then if you keep adding 1 to k, and eventually infinity, you should ideally have had more irrational, sorry, more
它上一期有邮箱嘛，这学期是 Google Form，
integers
就是
than
可以提。我刚刚看了一下，就
But
是
then usually
也有个选项是 reading。
Yeah, you can't apply induction to arbitrary infinite sets like that.
有 PPT 的。
It fails.
it struck me only now after so many years of
Yeah.
studying it.
So you're back from India, did you have any trouble? Or how's your, you have some family issues?
还 U PPT 出来。
But I'll be back.
所以快写完了已经。
一会儿还带点
吃的，
没什么看，
我也没吃。
撑得住。